Download this code from codegive.com, link in the description below. OK, let's dive deep into the concept of an dominating set in graph theory. This is a specialized and relatively less common concept compared to standard dominating sets. I'll provide a detailed explanation, including the definition, algorithms, properties, complexity, and code examples in Python. 1. Understanding dominating sets, the foundation. Before we tackle the n dominating set, let's refresh our understanding of the classic dominating set problem. Definition given a graph G equals V, E, a dominating set D is a subset of vertices D subset symbol V such that every vertex in V is either in D itself, or adjacent to at least one vertex in D. In other words, D dominates all the other vertices in the graph. Minimum dominating set. The goal is often to find a minimum dominating set, which is a dominating set with the smallest possible size. Finding the minimum dominating set is an NP-hard problem in general graphs. Example. 2. Introducing an dominating set. Now, let's define the n dominating set. It builds upon the idea of domination but introduces a specific logical condition. Definition given a graph G equals V, E, an n dominating set D is a subset of vertices D subset symbol V such that for every vertex V set membership symbol V, D, i.e., every vertex not in the set D. The set of neighbors of V, denoted as n, V, must be a subset of D. In other words, all the neighbors of V must be in D. This is where the n comes in, neighbor 1 and neighbor 2n. And neighbor k must be in D for V to be considered n dominated. Minimum n dominating set. The objective is to find the minimum n dominating set, which is the n dominating set with the smallest cardinality. Finding this set is also typically an NP-hard problem. Important considerations. A vertex in D is considered to be n dominated by itself, implicitly. Vertices with no neighbors are not considered n dominated, even if they are not in D. Thus, any n dominating set must include all isolated vertices. If a vertex V has only one neighbor U, then U must be in D for V to be n dominated. N domination is stronger than regular domination. If a set D is an n dominating set, it is also a regular dominating set. The reverse is not necessarily true. Example. 3. Algorithm and complexity. NP hardness. The problem of finding the minimum n dominating set is NP hard. This means there's no known polynomial time algorithm to solve it optimally for all graphs. Common approaches include brute force search. Generate all possible subsets of vertices and check if each is an n dominating set. Select the smallest one that satisfies the condition. This is only practical for very small graphs because the number of subsets grows exponentially, 2 sub v/sub. Approximation algorithms. Develop algorithms that aim to find good but not necessarily optimal and dominating sets within a reasonable time. The design of effective approximation algorithms can be challenging. Heuristic algorithms. Use techniques like greedy algorithms, genetic algorithms, simulated annealing, or local search to find n dominating sets that are good enough in practice. These algorithms don't guarantee optimality. Integer linear programming, ILP. Formulate the problem as an ILP, which can then be solved using an ILP solver, example Gurobi, Plex. This approach can be efficient for graphs of moderate size. Brute force algorithm, Python example. Explanation of the code. One is underscore an underscore dominating underscore set, graph, subset, asterisk. Asterisk. This function checks if a given subset of vertices is an and dominating set for the input graph. Asterisk. It iterates through each vertex in the graph. Asterisk. If the vertex is not in the subset, it checks if all of its neighbors are in the subset. Asterisk. If even one neighbor is missing from the subset, the function immediately returns false, because the condition for and domination is not met. Asterisk. If the loop completes without returning false, it means that all non-subset vertices are and dominated, so the function returns true. To find underscore minimum underscore and underscore dominating underscore set underscore brute underscore force, graph, asterisk. Asterisk. This function finds the minimum and dominating set using brute force. Asterisk. It generates all possible subsets of the vertices using bit manipulation, iterating from 0 to 2 caret, v, 1. Asterisk. For each subset, it calls is underscore an underscore dominating underscore set to check if it's an and dominating set. Asterisk. If it is, and if the subset is smaller than the current minimum, it updates the min underscore set and min underscore size. Asterisk. Finally, it returns the min underscore set, the smallest and dominating set found. 4. ILP formulation, integer linear programming. ILP can be a powerful tool for solving and dominating set problems, especially for larger graphs than brute force can handle. Here's how you can formulate the problem. Asterisk. Variables asterisk. Asterisk x underscore I, a binary variable, 0 or 1, for each vertex I set membership symbol v. Asterisk x underscore I equals 1 if vertex I is in the and dominating set D. Asterisk x underscore I equals 0 if vertex I is not in the and dominating set D. Asterisk. Objective function asterisk. Asterisk. Minimize the size of the and dominating set. Asterisk. Constraints asterisk. Asterisk. For each vertex v set membership symbol v. Asterisk x underscore v plus sigma x underscore u equals n, v, sum over all neighbors u of v. If v is not in the dominating set, x underscore v equals 0, all the neighbors n, v, must be in the dominating set in order for the and domination to hold, so the sum of their x underscore u values must equal the number of vertices in n, v. If v is in the dominating set, the constraint is trivially satisfied since x underscore v equals 1. Asterisk. Binary constraints. Asterisk x underscore I set membership symbol 0, 1 for all vertices I set membership symbol v. Asterisk. Python implementation using pulp library. Explanation of the ILP code asterisk. 1. Import pulp asterisk import pulp. 2. Define the problem asterisk prob equals pulp.lp problem, minimum and dominating set, pulp.lp minimize, creates an ILP problem object with the goal of minimization. 3. Create variables asterisk x equals pulp.lp variable.dix, x, vertices, cat equals pulp.lp binary, creates a dictionary of binary variables x underscore I for each vertex. 4. Objective function asterisk prob plus equals pulp.lp sum, x v for v in vertices, sets the objective function to minimize the sum of the x underscore I variables, i.e., minimize the size of the dominating set. 5. Constraints asterisk the core logic for the and dominating set condition is implemented in the constraints. The code adds the constraint described above for each vertex. 6. Solve the problem asterisk prob solve, solves the ILP problem using the default solver that Pulp has available. You might need to install a solver like CBC, Coin or Branch and Cut, if it's not already installed. 7. Extract the solution asterisk the code iterates through the vertices and checks the values of the solved variables xv.var value. If the value is greater than 0.5, close to 1 due to numerical precision, the vertex is added to the n_dominating_ set. 5. Properties and applications. Asterisk and domination is a stricter form of domination. Asterisk every n-dominating set is also a regular dominating set. Asterisk applications are less common than regular dominating sets, but might arise in scenarios where complete connectivity with a set of nodes is required, example in certain network design or security contexts. Imagine a communication protocol where a node only transmits data if all its neighbors are active in the network. 6. Considerations. Asterisk graph representation. Asterisk the provided code uses a dictionary to represent the graph. Other representations, such as adjacency matrices, can also be used. Asterisk solver choice. Asterisk for the ILP approach, the choice of ILP solver can significantly impact performance. Commercial solvers like Gurobi and Plex are often more efficient than open source solvers, but require licenses. Experiment with different solvers. Asterisk scalability. Asterisk brute force algorithms are only suitable for very small graphs. ILP can handle moderately sized graphs. For large graphs, approximation algorithms or heuristics are usually necessary. In summary, n-dominating sets are a more specialized concept in graph theory with stricter requirements than standard dominating sets. Finding minimum n-dominating sets is NP hard, but various algorithms, brute force, approximation, heuristics, ILP, can be used to find solutions depending on the graph size and desired solution quality. The ILP approach with pulp is a good starting point for moderately sized graphs.